Hi, my name is Song Park, and I'm gonna go through some papers I chose for a project, which are active learning helps pre-trained models run the intended task and on the trade-off between robustness and fairness. These are papers from active learning and fairness fields. So I'll start. These are the contents that I'm gonna go through. I'm gonna give some backgrounds of the papers, the problems the papers are addressing, and the methods the paper used to solve this problem. So I'll start with the active learning first. So I'll start with background first. Recently, there has been interest in machine learning that is using pre-trained models for new tasks with remarkably little data. And this process is often called as model deployment. However, there is one common challenge or failure in this procedure, which is encountering some unpredictable behavior. This failure can often be attributed to some um, can be attributed or referred to as task ambiguity, which means that the training data is not sufficient to fully specify the user's intended behavior for all possible inputs. So the training data is not good enough in quality or labeling quantity or labeling quality to fully capture the user's expectations. So in this sense, we can either increase training data, the number of training data, or improve labeling quality. But since our focus is on decreasing required training data numbers, so we have to find some ways to improve training data quality. Since labeling is expensive task, we want this labeling task to be as minimum as possible. One way to achieve this is active learning, which is asking the model itself to verify the data that needs to be labeled. I brought this diagram from the paper, and I'll explain what is active learning by this diagram. So here's here you can see some training data. There are lots of red squares, blue circles or ellipses, and we train model with this data to classify inputs into two distinct groups. So after training, pre-trained models would classify red squares and blue circles without difficulty. But when blue squares are given like this, the model is uncertain to whether to put it on red squares or blue circles because there are two um, features that it has. It is square and it is blue. So the model is uncertain to whether to focus on geometric shape or the color set. So active learning is asking this model to tell the user which input is ambiguous. In this case, it would be this blue square. The user can tell the model whether to focus on geometric shape or the coloring shape or the color. So, for example, if I say that you have to focus on geometric shape rather than colors, the model then can now distinguish blue squares and blue circles so they can classify training data with good accuracy. Despite of active learning's novel ideas, often its success in decreasing the training data was limited to specific task or distribution. It was sometimes even worse than just random sampling, which means that active learning had no advantageous effect in selecting the needed label. And this failure can be due to inappropriate label or too complex task for the model to solve, or just lack of information or experiences in designing active learning. And the author proposes that By pre-training models, these these challenges I just mentioned can be overcome because with neural networks, the complex tasks, lack of generality in error heuristics, or inappropriate labels can be approximated by some neural networks. So the paper show that pre-trained models can do better at active learning and verify this by comparing pre-trained models versus non-trained models on active learning. And also the paper compare pre-trained model with different datasets so that the more does it imply that the more they are pre-trained, the more they do better at active learning. For active learning, the paper uses this rule-based active learning, which says that it's most general method in active learning. This is pseudocode for rule-based active learning, although the notation are quite different from the paper. I just brought it because it's basically saying the same thing. So I'll describe active learning by this pseudocode. So they have set up initial label samples, which is R, and set up unlabeled samples, which is U. So neural network is trained based on these label samples. Then we pick some inputs that need to be that needs to be labeled. And how do we select? We use some sampling technique, and the paper used uncertainty sampling, which I will talk about it later. And then we give labels for that training inputs xi for and label it as yi. And since we labeled xi yi, it can be added to label samples, and we remove xi from new because it's not unlabeled anymore. Then we train your network based on these new sets of initial label samples. And yeah, that's how active learning goes on. A Gaussian function, which is function needed to select xi, that needs to be labeled as one approach called uncertainty sampling. Uncertainty sampling is sampling from points that are near the boundary. So the model is uncertain whether to so the model is uncertain whether it is group A or group B. So if we take example from this picture, it will be points near 2 based on this sampling method. And to be more specific, the paper used the least confidence sampling. And this least confidence sampling is one method in uncertainty sampling. The reason why it is called least confidence sampling because a Gaussian function is defined as -1 multiplied to confidence function of x. In this way, we can measure the uncertainty of given points and select based on this value. So I brought some example to explain this least confidence method in more detail. So we have x1. So we have training input x1 or x2. So the model predicts x1 label, which is y1 or y2, y3 with some probability, and x2 also. So based on these equations, um, this acquisition function for x1 would be minus 0.5, and acquisition function for x2 would be minus 0.4. So since x2 has higher acquisition function, x2 would be selected as the training input that needs to be labeled, because it's kind of straightforward, because in case of x1, it is predicting that x1's label is set to be y2 with probability of 0.5 with more probability. It is more certain with this result, but in case of x2, it is uncertain to whether to label it as y1 or y2 or y3. So yeah, this is one method of acquisition of function. So based on the methods I just mentioned, the paper is using BIT family model to compare the pre-trained models and non-trained models. They use BIT families and they pre-train them with different datasets. They are all on ImageNet, but one is ImageNet 1K, one is ImageNet 21K. Some parameters are different. So they compare with these ones and non-trained LessNet to show that active pre-trained learning helps active learning. And datasets to verify that is Oliver's iWorldCam 3%. So they check the accuracy of the classification, and they also check frequency of class to show how active learning is going on. So if one class is distinct, that kind of means that active learning is working well. Yeah, so I'll move on the trade-off between robustness and fairness. So some background before we move on to paper. There's adversarial training. Adversarial training is one method to increase robustness of model. This training is based on adversarial examples. For example, I wrote some images that show what adversarial training is. So we have image of panda, and we add some appropriate small noise to the image of panda and give it to model. And the model predicts this panda as gibbon, which is one kind of monkey. Even though if you look at it, we can really tell difference between these two images. This kind of example is called adversarial training. And nowadays, deep neural network is concentrating on more general tasks. It's kind of having same context with introduction of active learning. We want our model to solve general problem, even if the task is different or noise is added, or data distribution is shifted. So adversarial training is one method to make our model more general, more robust to adversarial attack, which is giving this kind of adversarial examples to our models. And the perturbation radius, which will be discussed in later slides, is kind of the scale of the noise added to input. In this case, it would be 0.007 in the picture. So there has been research going on this adversarial training, and one paper addressed that this adversarial training causes robust fairness phenomena, which is trade-off between robustness and fairness. Robustness is kind of straightforward, and I described it in earlier slides. But what is fairness? Fairness is consistency of performance between classes. For example, if the model is giving out consistent performance on all existing classes, we can say that this model is fair. But some models happen to be good at classifying some class, but extremely poor in some classes. Then this model is said to be unfair. In the paper, to be robust or to be fair, the paper addressed this kind of phenomenon, and they gave some framework to solve this problem by adding constraints to robust error difference between classes, so that the performance difference between classes is not too distinct. So that they are not too large. So the problem the paper is addressing that there has been no research on the effect of perturbation radius on this robust fairness phenomenon, even though this radius is one of the most important parameters in adversarial training. So the paper is wondering what kind of effect would perturbation radius have on this phenomenon. Would it increase or decrease? Why? And they gave some theoretical analysis and some better way to cope with this robust fairness problem. So the paper is kind of doing two separate experiments. One experiment is checking whether perturbation radius effects on robustness fairness phenomenon. They differentiate the perturbation radius and check if the robustness fairness phenomenon increase or decrease. So they use method algorithm called MADRI, which is one famous algorithm in this adversary training. And the models they used is LesNet 18, LesNet 15, WRN 3210, and datasets CFAR 10. And after they check that the higher the perturbation radius is, the more robust fairness phenomenon increases. They build up FAT verification. They come up with FAT algorithm, and they verify that their FAT is superior than original Madri algorithm. So they compare FAT with Madri. They use same model, LesNet 18, LesNet 15, WRN 3210, and they use datasets CFAR10 and CFAR100 to see if this FAT is good, better or not. To be more specific with the methods in adversary training and the way they solve this problem, I brought some equations in the paper. So the first equation is that what we usually saw in machine learning. We are training our neural networks so that we hope to find the classifier F nature with the smallest natural risk, which is R nature. However, in adversary training, we have different Z that is elements of U. U is perturbation set. So we saw that adversary examples and Z is kind of those adversary examples. So we are trying to find out classifier that are robust, that that are robust or that have minimum expected loss in those adversary examples. And the paper proposes this kind of FAT algorithm, which stands for Fairly Adversary Training Algorithm, to mitigate the trade-off between average robustness and robust fairness. So in these equations, this is empirical risk, what you saw earlier, and this is some new parameters and some new definition to stand for disparity, the fairness thing. So this PCA PCAR is defined in this way, in which corresponds to the last line, and PCAR stands for variance of class-wise adversary risk. So we are kind of so we are making variance between average of adversary a average risk of F on adversary examples and some specific risk of adversary examples on specific classes. So I stands for some classes, and we are summing them up. And some regularization factor in front of it to properly show this variance. Yes, so based on these methods, they build up their algorithm and do some experiments based on this. So more detailed experiments and the results are gonna. So this is just presentation. I just went through some backgrounds. I will put more um, specific figures and experiments in final report. Thank you.